Hey guys, this video is about work, the Nernst Equation, concentration cells, and electrolysis. So when an electrochemical cell does work, that it does work by moving electrons through a wire, right? And so we say we drive an electric motor or something like that. The amount of work that can be done by moving those electrons through a wire depends on what's called the electromotive force, which is defined by the potential difference between any 2 points in the circuit. Those 2 points would be each half cell. And so the electromotive force, potential difference, is the amount of work that it can do divided by the charge that's transferred. In terms of symbols, E, which stands for our cell potential, is equal to negative W, work, over Q, total amount of charge that is transferred through this circuit. Now, we define work done by the cells being negative, and so that means that this negative sign here makes the cell potential positive when the cell does work. Now, when that does happen, when an electrochemical cell does electric work, it has to push an electric current through a wire. It must flow through a wire. And when that happens, there's always frictional loss. What does that mean? Well, when an electric current travels through a wire. Now, by the way, we're not talking about superconductors here. That's a different class. We're talking about regular copper wire, for example. There's always frictional loss. And what frictional loss is that as that electric current passes through that wire, some of that energy is converted into thermal energy, heat. And so we increase the amount of thermal energy of the surroundings, and that amount of energy that goes into creating thermal energy is lost. We can't use it to do work anymore. And so that means that for any real process, the work that we get out is less than the calculated maximum amount because we lose some to thermal energy. This is actually a demonstration of the second law of thermodynamics, which says that for a process to be spontaneous, the entropy of the universe must increase. So as that electric current passes through the wire and it heats up due to frictional losses, the thermal energy that's lost goes into increasing the temperature of the surroundings, which increases the entropy of the surroundings and thus the entropy of the universe. That happens for a spontaneous process. Now, the total amount of charge that passes through that wire, it's just the total number of moles of electrons that pass through the circuit times some constant. So if n is the number of moles of electrons that are transferred, and the constant is this F, right? It's called Faraday's constant. And Faraday's constant, guys, is just defined as the charge on exactly one mole of electrons. So the value for Faraday's constant is 96,485 coulombs amount of charge per mole of electrons. This is not an exact number, by the way. It's 5 sig figs, which will be enough for us. Now, because we know that 1 volt is equal to 1 joule per coulomb, or a coulomb is equal to a joule per volt, we can also write the units for Faraday's constant as joules per volt mole of electrons. That's useful a lot of times. So, because the maximum voltage the cell can produce, it gives us a maximum amount of electrical work we can get from that reaction, we can write that the W max, the maximum amount of work, is equal to the total charge times the cell potential. If you look at the units here, it probably helps to see how it works out. Remember, n is the number of moles of electrons transferred. Faraday's constant is, think about this with units of joules per volt mole of electrons. So moles of electrons cancel already, and the cell potential is volts. So volts cancel, and we end up with joules. So this gives us joules amount of work. Now, we also saw, guys, back when we talked about Gibbs free energy, that we can calculate the maximum amount of work any process can do by delta G, because both delta G and negative NFE cell are equal to the maximum amount of work. They're equal to each other. Now, real quick, let's look at signs here. We know that for a process to be spontaneous, delta G must be negative. When we look over here, because of this negative sign, that tells us that for a cell to run spontaneously, its cell potential must be positive, because that gives us a negative delta G. So now, actually, so sort of as an aside, guys, we've seen now three different, I guess, criteria for spontaneity. The big one that we started with, what's still true, of course, is that for any process to be spontaneous, the entropy of the universe must increase, must be positive. Then we saw that for a process to be spontaneous, delta G for that process must be negative, less than 0. And now we see that for an electrochemical cell, for that cell to run spontaneously, the cell potential must be positive. So now if we put everything in there under standard conditions, right, we can say that delta G 0 equals negative NFE 0 cell. We also know back, guys, from when we talked about Gibbs free energy, that delta G 0 equals negative RT ln K. So both of these are equal to delta G 0, so let's see what happens if we set them equal to each other. Well, first thing that happens is this negative sign cancels, all right? So we have NFE 0 cell equals RT ln K. Now if we divide through by NF, we can isolate E0 of the cell. So it ends up being equal to RT over NF ln K. This is a pretty useful relationship. E0 of the cell is something we can calculate or measure, and that can give us directly an equilibrium constant, which is pretty cool. Now, most of the time we talk in electrochemistry, we talk about processes happening at 25 Celsius. So if that's true, 25 Celsius, or say 298.15 Kelvin, we can plug in, okay, all these numbers here except N. So R is 8.3145 joules per Kelvin mole. At 25 Celsius, temperature will be 298.15 Kelvin. Faraday's constants, 96,485 joules per volt mole. We'll plug all those in, and we get RT over NF. This ratio here is equal to 0.02569 over N, the number of moles of electrons transferred in that process. So if we plug this in here to E0 of the cell, we get E0 cell equals 0.02569 over N, natural log of K. Now it ends up that in electrochemistry, when they discovered all this stuff, they liked to use log base 10 rather than natural log. So to convert the natural log to log base 10, which is what we traditionally do, it ends up that natural log of a number is 2.3025 and some more numbers times log base 10 of that number. So if we use this, then we can put it into this right here, convert natural log to log base 10. We see that E0 of the cell equals 0.05916 over N, the number of moles of electrons transferred, times log base 10 of K. Now, real quick, guys, if we are not at 25 Celsius, that's easy. Then we just come back up here and we use RT over NF. We just plug the values in with the actual temperature here, and we multiply this by 2.303. So we get 2.303 RT over NF log base 10 of K. Or I guess if you wanted to use natural log, you could do that too, but it's just sort of tradition, I guess. We use log base 10 in electrochemistry. All right, so now we're going to do an example. We want to calculate delta G0 for this process and K, the equilibrium constant. And this, so what this is this, think about this as an electrochemical cell, because that's what we're talking about, where we have two half cells, one the anode where oxidation is happening, one the cathode where reduction is happening. So here, nickel is going to nickel plus 2. That's oxidation. That half cell would be the anode. Lead 2 is being reduced to lead. That's reduction. That would be the cathode. So if we look up the potentials for the half reactions in this table of standard reduction potentials, they're all reductions in here, we see that for lead 2, the standard reduction potential is negative 0.13 volts. And for the reduction of nickel, the reduction potential is negative 0.23 volts. So remember, when electrochemical cell runs spontaneously, the half cell with the more negative or at least positive half cell potential, it's reversed, becomes the oxidation. So if we reverse this, then we get what's happening up here. And remember, guys, when we reverse a reaction, we change the sign of the potential. So we're going to do that right now. So there's our reaction. There's the half reaction, the reduction half reaction, lead going to lead, lead 2 going to lead. Half reaction potential is negative 0.13 volts. This is the reduction potential for nickel that we looked up in the table over here. We reverse this, make it an oxidation half reaction, and we change the sign of the cell potential, half cell potential. And so to get the E0 for the cell, for the reaction, is just E cathode plus E anode, which ends up being a positive 0.10 volts. So positive E0 cell, spontaneous, at least under standard conditions. And this is just writing this electrochemical cell with line notation. So we would make the electrode, the anode half cell, out of nickel. Well, we could use platinum, as probably nickel's better. And in solution we'll have nickel 2, salt bridge or porous plug. In the cathode we have lead 2 in solution and a lead electrode. So remember, we want to calculate delta G0. So that's just negative NFE0 cell. We got E0 of the cell, positive 0.10 volts. F, we know, Faraday's constant, 96,485 joules per volt mole of electrons. Now N, okay, so this is where you have to be a little bit careful. N is how many electrons are transferred in the balanced electrochemical reaction. Here, each half reaction has 2 electrons, so it's 2 electrons that are transferred. Now, if let's say one was 2 and one was 3 electrons, then we'd have to get the least common multiple, which is 6, and that's how many electrons would be transferred. In that case, N would be 6, but here it's just 2. Right? So anyway, so we calculate delta G0, negative 119.2 kilojoules. Okay. Now, that gives us our delta G0. Okay, we got that part. To get the K, we use the fact that delta G0 equals negative RT ln K. Delta G0 is negative 19.2 kilojoules. The negatives cancel here, and we plug our values in. So I use 0.008345 kilojoules per Kelvin mole for my R. We're at 25 Celsius at 298.15 Kelvin. And we see that natural log of K is equal to 7.78. Where K is equal to E to that, inverse natural log, or 2.4 times 10 to the third, or 2,400. So yeah, pretty large K. It's going to go pretty easily in the forward direction. Okay, the Nernst equation. It's a beautiful equation. You're going to love it. So we know from the Gibbs free energy module that delta G is equal to delta G0 plus RT ln K, right? But we also know that delta G0 equals negative NFE0, and likewise delta G equals negative NFE. So all we do to get the Nernst equation, guys, is replace each of these delta G's with the appropriate negative NFE. So we get negative NFE equals negative NFE0 plus RT ln Q. And then if we divide through by negative NF, we get basically the Nernst equation. E equals E0 minus RT over NF ln K. But once more, we're going to use log base 10. So we have E equals E0 minus RT over NF 2.3025 log base 10 of Q. And then once more, at 25 Celsius, we can plug in for all these the constants and the temperature, and this ends up being E equals E0 minus 0.05916 volts. The units here end up being volts over N, which is the number of moles of electrons transferred times the log of the reaction quotient, Q. Now, we'll see this in just a second, but just real quick, notice that, so this is the Nernst equation. At equilibrium, E is equal to 0, and Q becomes K. And so we can say E0 equals 0.05916 over N log of K. So let's look at this electrochemical cell, this galvanic cell, guys. So here at the anode, we have, where oxidation is happening, we have the iron 2 ion being oxidized to iron 3. Okay, platinum electrode. We could have used iron, I guess. But then that would have iron actually we couldn't, because then that would complicate it with the stuff that's going on down here. So platinum's better. Connected with a wire, we have a silver electrode and the silver ion in solution here. All 1 molar, so standard conditions, but we can change that. And we have a porous plug, right? So the overall electrochemical equation is the iron 2 going to iron 3 and silver being reduced to silver. So if we look up the standard reduction potentials, and then get the oxidation potential here. So if we look down here, So I know you can't see it, but back on the big one, we could. So the standard reduction potential for iron 3 to iron 2 is positive 0.77 volts. So for the oxidation from +2 to +3, it's negative 0.77 volts. And the standard reduction potential for silver ion going to silver is 0.80 volts. So E0 of the cell is equal to just E cathode plus E anode, which is 0.80 volts minus 0.77 volts, or 0.03 volts right here. So now that we know E0 of the cell, okay, we can use this in the Nernst equation and see that the E of the cell is equal to E0 0.03 volts minus 0.05916 over N. In this case, N is 1 because one electron is being lost when it's oxidized from iron 2 is oxidized to iron 3, and one electron is gained when silver is reduced to silver. So N is 1. And log of the, of Q, which is products over reactants. So the solids do not appear. So we have concentration of iron 3 here, concentration of iron 2, and concentration of silver in the bottom. So you see what happens is when we connect these two electrodes with that wire, electrons start to flow right away. And as that proceeds, what happens is the concentration of iron 3 increases. In the anode, we oxidize the iron 2 to iron 3. We increase the concentration of iron 3. Now we're still balancing charge with the porous plug here, but concentration of iron 3 increases. Concentration of silver ion is reduced. And also, because iron 2 is being oxidized to iron 3, the concentration of iron 2 also decreases. So we see that the denominator here is getting smaller and the numerator is getting larger. So this term here is becoming larger. And so because of this negative sign, we start reducing the cell potential. It becomes less than 0.03. And this keeps going until the concentrations are such that this term balances E0, and now E equals 0. We're at equilibrium, the reaction stops, Q is equal to K. And at that point, E0 equals 0.05916 volts over N log of K. Now, at equilibrium, E0 equals 0.05916 volts over N, in this case 1, log of K. But we know E0, it's 0.03 volts. So what we can do, guys, is we can solve this equation up here, form of the Nernst equation, basically for K, right? And so this is how it works. We get log of this is equal to 0.03 divided by 0.05916, and I guess multiplied by 1, but that doesn't do anything. Or we get about 0.5 for the log term. Take 10 to both sides, and we see that this ratio, which is K, is equal to 3.2 or so. What that tells us in terms of electrochemistry, though, is that if we set a cell up, the two half cells up, so that the ratio is greater than this number 3, the concentration of iron 3 over iron 2 to silver, if the ratio is greater than about 3, then the reaction will not run in the direction written, but it will run spontaneously in the reverse direction. Right? So there's that. Now let's talk about concentration cells. It's possible to construct an electrochemical cell where each half cell has the same ion in it, just different concentrations, right? For example, the cell described by this line notation. The anode, where oxidation is happening, we have a copper electrode, copper 2 ion in solution at an initial concentration of 0.050 molar, salt bridge, and then in the other half cell, where reduction is happening in the cathode, we have copper 2 ion also being reduced to copper, which is the copper electrode. This is 2 molar. So we have a dilute solution and a concentration solution. And so first of all, guys, for a concentration cell, it's both half cells have the same ion in it. The only difference is they're at different initial concentrations. So whichever half cell is more dilute, has the lower concentration, that will always be the cell that's the anode, where oxidation is happening. And the half cell that has the greater concentration of that ion, will always be the cathode where reduction is happening. Because what happens spontaneously is, see, these two concentrations, they want to become equal, right? So at the anode, okay, if we oxidize the copper to copper 2, we increase the amount of copper 2 ion until we get to, where it's trying to become 2 molar, right? So we oxidize it, we lose 2 electrons. On the other hand, in the other half cell, the cathode where reduction is happening, those 2 electrons are reducing the copper 2 ion in there, and that 2 molar solution of copper 2 is trying to become 0.05. Now it's going to meet in the middle somewhere, right? And when it does, it stops. Which, by the way, happens really quickly. So in a concentration cell, if you just set it up and let it run, within probably a few minutes, usually it stops because the concentrations have equalized. Now, in a concentration cell, E0 is equal to 0 because E0 of the cathode is equal to E0 of the anode. They're both copper 2, and standard conditions means 1 molar. So whatever the cell potential is for copper 2, it's the same in both half cells. So because E0 is equal to 0, now E of the cell is equal to, this term goes away, is negative 0.05916 volts over the number of moles of electrons transferred log base 10 of Q, which is the concentration of the dilute solution over the concentration of the concentrated solution. So in this case, if we plug in the concentration of the dilute solution, again, this is before any electrons flow, as 0.050 and the concentrate is 2, we can get a number. We see the E of that cell is positive 0.047 volts. It's positive, it'll run spontaneously until these are equal and this becomes 0. This becomes 1 and log of that becomes 0. Now, we can use a concentration cell by measuring the cell potential of a concentration cell like this example here. You'll see we can use it to measure KSP, which is pretty cool. So electrochemistry is a large field of analytical chemistry. We can do a lot of analytical chemistry with electrochemistry. And so we're setting up this cell. There's a line notation, a copper electrode, a saturated solution of copper 1 chloride. So that means that it's saturated, which means that we have the most of the copper 2 chloride dissolved as possibly can at that temperature. This is going to be 25 Celsius. Salt bridge, we have a solution of copper 1 nitrate, not copper 2, copper 1. Copper 1 nitrate over here, and it's at 1 molar. We don't care about the nitrate, guys. This is a spectre ion. Basically, this is copper 1 ion, right? So this is the concentration cell. In one half cell in the anode, we have copper 1 ion. This saturated solution is going to have a very small concentration of copper 1. Over here, it's 1 molar, a lot greater, right? So both copper electrodes. So what we do is we set this up, and then we measure the cell potential with a voltmeter. And we get positive 0.177 volts. What's the concentration of copper 1 in the copper 1 chloride compartment? And given that, we will be able to find KSP. So I want you guys to see if you can do this. I'll give you a couple, pause the video and then come on back when you get an answer. But so the idea is that we can use this measured cell potential and what we just saw with the Nernst equation for a concentration cell to solve for the ratio of the concentration in the diluted cell versus the concentration in the concentrated cell. We know the concentration in the concentrated cell, 1 molar, so we can solve for the concentration of copper 1 in the saturated solution, which is the dilute cell. We get that, and that's S. So going back to our solubility module, because it's KSP is equal to just concentration of copper 1 times the concentration of chloride, which is S squared. We can solve, when we get the concentration of copper 1 in this half cell, that's equal to S, square that, we get our KSP. All right, go and do it real quick, guys, and come on back when you get your answer. Welcome back, guys. So, here we go. Nernst equation, which remember for a concentration cell, E0 equals 0, so it's just E equals negative 0.05916 volts over N. Log of the diluted concentration over concentrated concentration. N is 1 because it's copper 1 being reduced to copper and copper being oxidized to copper 1. So this is equal to 0.177 volts. So we can solve this for, set this up, solve this for the concentration of the copper in the dilute cell. So if we do this, we, so basically just divided by negative 0.05916 volts, we get log of this term is equal to negative 2.99, or taking 10 to both sides, concentration of copper over the concentration of the concentrated cell. Now it's 1 molar here, but it doesn't have to be, it can be whatever, right? And this is equal to 10 to the negative 2.99, or 1.08 times 10 to the minus 3. Then if we multiply through by this concentration, which happens to be 1 molar here, but it doesn't have to be. So we get the same number in this case, but only because this concentration was 1 molar. Anyway, so we get the concentration of copper 1 in the dilute cell, the saturated solution, as 1.018 times 10 to the minus 3 molar. And because this is the equilibrium, KSP is equal to the concentration of copper 1 times the concentration of chloride, which is S squared, which is just a concentration of copper 1 squared, which ends up giving us KSP of 1.04 times 10 to the minus 6. Pretty cool, huh? All right, so now the last topic in this module is electrolysis. So in electrolysis, basically we hook up an external power supply and force a galvanic cell to run, well, it's not galvanic anymore, the electrochemical cell to run in the opposite direction than it would spontaneously. So if we look at this picture down here, we have the anode. In the anode there's zinc ions, right? We have a zinc electrode. In the cathode, where reduction is happening spontaneously, we have copper 2 being reduced to copper, the copper electrode. Again, sulfate's just spectator ions. And so if we measure this cell potential, it ends up it's 1.10 volts, right, under standard conditions, E0. So now for electrolysis, guys, what we do is we hook up a power supply in the circuit and direct the current in the, force the current in the opposite direction with a greater potential than 1.10 volts. So when now the current flows in the opposite direction and the copper is being oxidized, it now becomes the anode. The zinc is reduced, it becomes the cathode. We have to force this to happen, right? But when we do this, there's some really cool things we can do. Once more, applications in analytical chemistry. So remember that the electrical current is, the unit is 1 ampere, which is 1 coulomb per second. So if we know what the current that's flowing is, and we measure how long that current has been flowing, if we take the current, coulombs per second, times the time in seconds, we get the total amount of charge that's been pushed through that circuit. In this case, the total amount of charge that's reducing the zinc ions to zinc metal, right? And if we take the total charge that's transferred and divide by Faraday's constant, which remember is the charge per mole of electrons, we'll get how many moles of electrons were transferred through the circuit, were pushed through the circuit. And now, if we know how many moles, the ratio of how many moles of the species that are reduced per mole of electrons transferred. In other words, like, this is not as complicated as it sounds. If we have a +2 charge over here, then it's going to be 1 mole of zinc is reduced for every 2 moles of electrons transferred, because we need 2 electrons to reduce zinc to zinc, or zinc with a +2 charge to zinc. So that would be a 2 down here, for example. But if we do this, we get how many moles of the species is reduced, which means that if we know that, we can, for instance, we can calculate how many grams, if we know what it is. If it's a solid, we know its molar mass. If we know how many moles, multiply by the molar mass, we can get how many grams would plate out. We call this plating out, because what happens is the ion that's being reduced in the electrolysis cell actually plates out. It coats the surface, which is how they chrome things. When the chroming process is just an electrochemical cell where they plate out chrome ions onto the surface of whatever they're electroplating. Also, another application of electrolysis is with not a solid, but with gases. You can use this to dissociate water into hydrogen gas and oxygen gas, right? And so that's really neat, because if we can take just plain old water, break it into hydrogen gas and oxygen gas, separate them, now we have a source of energy, right? we can combust that hydrogen and oxygen, and maybe put it in an engine. But there's a catch, okay? The second law of thermodynamics. It ends up that it will always take more energy to break apart that water into hydrogen and oxygen gas than we would get back out by combusting that hydrogen. So it costs more to make it than we can get by burning it. But there's a lot of research being done nowadays with you figuring out ways to use sunlight to power this, so it doesn't cost us anything to electrolyze water. Using catalysts to make that happen in the sunlight. There's all kinds of interesting stuff going on. Another thing, by the way, that we can do that, guys, is if we know the current and the time, we can calculate the moles of electrons. We know if we measure the mass that gets plated out, so that's real easy. All we do is we measure the mass of the electrode before the experiment, turn off the current, then measure the mass of the electrode afterwards. The difference is the mass that's plated out. It ends up, and you'll see this in a minute, we can use that to calculate the molar mass of whatever's in solution here. All right, so let's do some examples. An example, rather. So we have some unknown metal, right? It's electrolyzed. And it took 74.1 seconds with a current of 2.00 amps to plate out 0.107 grams of metal from a solution that contains the, we know, so this is the metal, whatever it is, it's, and with nitrate. So we know already this has basically a +3 charge, okay, and that's important. What's the metal? So if we can figure out the molar mass, we can figure out the metal. So the idea is we know the current, we know the time, so we can get the amount of charge. And we know that there's 1 mole of metal reduced for every 3 moles of electrons transferred, so we can get the moles of the metal. We know the grams of the metal, so we can grams over moles is molar mass. So why don't you guys work that out real quick and come on back when you get your answer. Welcome back, guys. So take the current, 2 amps to 2 coulombs per second times the time, 74.1 seconds, and we see that 148 coulombs of charge have been passed through that circuit. So we take the charge divided by the charge per mole of electrons, Faraday's constant, and we see that we transferred 0.00154 or so moles of electrons. And because this is a plus, we know this is a +3 ion, that means 3 moles of electrons were transferred. So we have this many moles of electrons transferred times 1 mole of the metal per 3 mole gets reduced or plated out. For every 3 moles of electrons transferred, we see that we plated out 5.12 or so times 10 to the -4th moles of the metal ion becomes just metal with no charge. And so the molar mass is just the mass divided by the moles, 209 grams per mole, which ends up being bismuth. And that's all there is to that, guys.